Okay, for today's class, we're going to start with this warm-up. So I am going to get you guys to pause the video and work on the warm-up. For each of the questions, you do need to pick a number and or a function or two. So for the first one, you're just picking a number k, any number that you want, and then you're going to find f prime of x or the derivative of f at x, or you could be thinking about that as the IROC. You're using your limit of the difference quotient to find the slope of the tangent at any point x on that equation, f at x equals k. And then in number two, you're picking the number n, which is going to be the exponent on x. So we're trying to find what is the derivative no matter what exponent I pick on x. And we should be finding a pattern. So I'd like you to try to compare these answers with your neighbors. And then number three, you're trying to pick a number k, that's going to be the coefficient, in front of a function g at x that you know. So it could be like a number -3 in front of a g at x could be x cubed or something like that. And then number four, we're picking two functions, p at x and q at x, and we want to figure out, well, what's the derivative when I add those two functions or when I subtract those two functions. So you might want to pick two functions that we're more familiar with. So maybe you pick x squared. We already know that the derivative of that is 2x. And maybe you pick the one that you also picked already in number two. And then just taking the derivative now as an addition and as a subtraction. So pause the video and go ahead and do that. Okay, so hopefully that you finished that up and you've done your investigation. What we're looking at here is when I pick a number k, so I'm picking some number, like maybe I pick -5. When I take the derivative of that, and I'm using my limit formula, so I'm doing that the derivative is equal to all of this jazz. But now when I'm subbing in x plus h into my equation is f at x equals -5. There's nowhere for me to sub in x plus h. So I'm going to just get -5. And then same thing for the second part, just subtracting my original function. My original function was -5 here. And so what I get here is 0 over 0. And there's no h for me to factor out. So I'm going to end up with taking the limit as h approaches 0 of 0 over h. And so I'm kind of stuck here. But I'm imagining h getting really close to 0. So what I can do here is take the left-sided limit and the right-sided limit to evaluate this because I can't simplify the h away. And when I take a look at coming in from the left-hand side, this is approaching 0. And coming in from the right-hand side, this is also approaching 0. So I can say here that the derivative is always going to be equal to 0. So the slope of the tangent line is always going to be 0. We're going to talk about why that makes sense in the next slide. The next one, I'm picking a number n, so I'm picking my exponent. So perhaps, and hopefully you didn't pick 2 here because we've already looked at that function, but maybe you looked at picking like x to the power of 4 or something like that. Or maybe you picked a negative, so I'm going to look at a second example. Maybe you looked at x to the power of -3. And what you should have found going through the limits for these two examples is my f prime derivative would come out as 4x cubed, and my my g prime, so the derivative of g at x, would come out here as -3x to the -4. And we're looking for some patterns, like how did I do that in my head without having to calculate the limit? In number 3, you're picking a coefficient as well as a function g at x. So perhaps you chose one of the functions that we'd already looked at. So maybe I'm using x to the power of 4 again, and then I'm just picking some coefficient. So maybe I'll pick my -5 like I did in question 1. When you find the derivative of this, again, you're looking at using your limit formula, and what you should find here is that your derivative comes out to -20x cubed. And again, you're looking for some patterns, like how did I know that without having to go through my limits? And those are going to be our shortcut tricks. So likewise, we could have used our g at x from above, but added a coefficient in front. So maybe this time I add, not add, but multiply by -2. And then when I take the derivative this time, I'm going to get 6x to the -4. And so again, looking for some patterns there. At the bottom of the page, picking two functions, p at x and q at x. So if I pick p at x is x to the power of 4 and q at x is x to the power of -3, then I can take the derivative. My f at x would be x to the power of 4 plus x to the power of -3. And again, I'll take the derivative using my limits, but what you should come out with is 4x cubed minus 3x to the -4. And then similarly, if I did the g at x as the subtraction, then when I take the derivative, my result should be 4x cubed plus 3x to the -4. So the pattern there that I can see is that by adding the two functions or subtracting the two functions, the derivative is really just the sum or the difference of the two derivatives. So I can take them separately and then do the addition at the end if I'd like. So we're going to summarize in our note today. Today we're talking about the derivatives of polynomial functions. And so the first rule that we have is our constant function rule. So if f at x is equal to some constant number, so we're just picking a number for k, then the derivative is always going to be equal to 0. Another way for me to write this would be dy dx, that's my Leibniz notation, and I would say that it is equal to 0. So why does that make sense? So let's take a look at an example. So if my f at x function is equal to -2, I can imagine what the graph of that would look like. Well, this is just a horizontal line at y equals 2. And so if I'm finding the slope of the tangent along that line at any point, of course the slope of the tangent is going to be 0 because the slope of the whole graph is 0. And so that's why that rule makes sense for us. The next rule we're going to take a look at is the power rule. So this is going along with our warm-up question number 2, where we picked lots of different powers on our x. So we've got f at x is equal to x to the power of n. N is some real number. Then I can always find the derivative, I hope you notice this pattern, by bringing the exponent out front and making it a coefficient, and then just subtracting 1 from my old exponent. And so this is our power rule. So I can use this rule to find the derivative of each of these examples. So for the derivative of f, I'm just changing my notation to say that I am now finding the slope of the tangent instead of the original function. And here I'd bring the exponent out front. So now my coefficient is 5. And then on the x, my exponent becomes 1 less. Likewise in g, when I take the derivative of g, I want to bring the exponent down front. Now this original function looks like 1 over. So in order to use my power rule, I'm going to move the x to the numerator. And to do that, I'm just using my negative exponent rule. So -4 is the exponent on this one. So now I can use my power rule for derivatives and bring that exponent out front and then just subtract 1 from my exponent. And I could rewrite that if I wanted, taking that negative exponent on 5 into the denominator. So -4 over x to the power of 5. And then finally taking the derivative of h at x. Again, I can bring that exponent out front. It becomes the coefficient. And then I need to subtract 1 from the denominator, or from the exponent. Notice that I'm subtracting 1 here. I want to make a common denominator. So I'm subtracting 2 over 2. And so my resulting exponent is 3/2. The next rule we're going to talk about is the constant multiple rule. So this is just what happens when I have a constant or a coefficient in front of another function. And what you should notice here is that you are just taking that constant, leaving it out front, and then multiplying it by the derivative of the other function. So the constant just kind of hangs out until the end, and then we'll simplify it into that derivative. So I can take a look at a couple of examples here. In my first one, f prime at x, my constant, or my k value, is 5, and then my function g at x is x to the power of 6. So the 5 is just going to hang out until until we find the derivative of x to the power of 6. So we're using our power rule to find the derivative of x to the power of 6. We bring the power out front and then subtract 1 from the exponent. And then I can simplify this all together. In g at x, again, I'm doing the same thing when I do g prime at x. My coefficient is 8. I'm just going to leave that and take the derivative of the next piece, x to the power of 3/2. So using my power rule, I bring the 3/2 down. And then for my new exponent, I'm subtracting 1. So again, subtracting 2 over 2, and I'm left with x to the 1/2. And I can simplify that. I've got 8 over 2, which gives me 4. So now I'm left with 4 times 3, which is 12. And then instead of writing x to the power of 1/2, I could change that to the square root of x. Our next rule is the sum and difference rule. So this one here, I've got two functions, p at x and q at x, and it's important that they are differentiable, which means, again, I can take the derivative of those two functions. And whether I'm using the sum or the addition, so I've got both of those symbols, f at x is equal to p at x plus q at x, or if it was subtract q at x, then I can just take those derivatives separately, p prime at x and q prime at x, and then I can either add or subtract whatever the original was to find my result. So we'll take a look at these two examples here. The first one, I don't have two functions being added or two functions being subtracted. I actually have two functions being multiplied. So I'm going to expand this out so it becomes a subtraction or addition statement. So just foiling out these two brackets, I'm going to get 9x squared, then I'm going to get negative 3x minus another 3x, so negative 6x, and plus 1. So just writing my function in a different way makes it a little bit easier for me to take the derivative. So now taking the derivative, I've actually got three pieces that I'm either adding or subtracting together, but I know that I can take the derivative of each piece separately. So the 9 is just hanging out, it's a coefficient, and then I'll take the derivative of x squared, which we know from yesterday was 2x. And then the next one here, I've got negative 6. It's just going to hang out, and then I'll take the derivative of x. Don't forget there's a power of 1 on that x. So I bring the 1 down front, and then I subtract 1 from the exponent. So now it's x to the power of 0. And then finally, we've got plus 1. We know that when we take the derivative of a constant, the slope is 0. And then I can simplify this. So I've got 18x, and then minus 6, and then multiplying by 1 times x to the power of 0. Remember, x to the power of 0 is equal to 1. So I'm really just multiplying by 1 there at the end, and I'm done. For our next function, again, I'm going to just rewrite how this looks because I need to use my power rule. So my first one, instead of having x in the denominator, I'll bring it up and give it a negative exponent. And then I'll take the derivative. Again, leaving my coefficient out front, and then just taking the derivative of x to the power of negative 1, bringing that exponent down front, and then subtracting 1 from the exponent. Leave my coefficient out front, and then take the derivative of x cubed. And then I'm just going to simplify. And I could leave it like this, or if you'd rather, you can bring that negative exponent into the denominator and write it like that. And for your homework today, we're going to skip this one for today. I'm going to go through that one on Friday. Or on Monday, sorry. Page 82, numbers 2 through 6, 9, 10. Don't forget to start your summary sheet. We've got 2 lessons out of 5, so we're almost halfway through, and then a couple of challenge questions. Have a good day, guys.